Now we will see the phenomena that causes the formation of energy bands in a solid. So this is the atomic configuration for silicon atom. Here we have 4 valence electron, 2 electrons in 3s orbital and 2 electrons in 3p orbital. For an isolated silicon atom, in 3s orbital there are 2 states that electron can occupy and it is filled with 2 electrons. So there are 2 states available and it is filled with 2 electrons. For p orbital, there are 6 states available, 2 states each in px, py, pz, but we have only 2 electrons filled. So there are 6 states available and only 2 electrons filled. So this is for isolated atom. If such n silicon atoms comes close to each other, then what will happen? There will be total 2n states available in s orbital, 3s orbital and 2n electrons are filled. Similarly, in 3p orbital there will be 6n states available and 2n electrons filled. This is for n number of atoms. When these n number of atoms are far away from each other, they don't see the effect of each other. When they start coming close to each other, they start to feel the effect of electromagnetic field of the other atoms nearby. When the separation between these atoms becomes very low, the outer orbital of the atoms start merging. Suppose these are two atoms. So what will happen when they will come close? The outer orbital of these atoms start overlapping with each other, and this overlapping causes interference between the orbitals. So this interference can be positive interference or the negative interference, causing the shift in the energy level of the orbitals. Also, the electrons in these orbitals come very close to each other. They want to occupy the same space, but this is not possible. Here electrons are negatively charged, so they will feel the repulsion force of each other and the attraction force from the opposite nucleus. So these forces and the overlapping of the orbitals will cause the shift in their energy levels. So all these electrons will have different energy levels. The more they come closer, the more will be the overlapping of these orbitals and more number of electrons will come closer to each other. So there will be more and more shift in the energy level, and this shift in energy of the electrons will create many more new energy states that are different from the original atom that was isolated. We can understand this phenomena with a plot of energy versus interatomic distance. When distance is large enough, all the atoms are isolated. They will have these energy levels 1s, 2s, 2p, 3s and 3p. The electrons in the lower energy level will be bounded to the nucleus, that they cannot participate in the bonding when the atoms come closer. Only the valence electron, that is 3s and 3p electrons, will participate. We have seen it here. For n number of atoms, there will be 2n states available and 2n electrons filled. This is for 3s orbital, and for 3p orbital 6n states available and 2n electrons filled. Here 4n states are empty. When these n atoms start coming close to each other, due to the overlapping of the orbitals and close proximity of these electrons, there will be shift in energy levels. and new energy level will be created that will not be same as the original energy level, but it will be near to that energy level. So less the distance, more and more will be the overlapping, and more number of energy levels will be created. And this also increases the range of the energy level associated with the electrons that are overlapping. So more and more overlapping, more and more widening of this range. Same happens with 3s electrons. A time will come when the outer orbit of the atoms will be fully overlapped, and all the electrons will have different energy states than their original energy states. So how many states will be available here? 6n plus 2n, that is 8n energy states will be available, and 2 plus 2 4n energy states will be occupied with 4n electrons. We can say this is band of 8n energy states here having 4n electrons. When the distance is further decreased, this band splits in two bands because of the bonding between the atoms. All these 4n electrons will participate in bonding and will occupy this lower energy band to stabilize the structure. This fully occupied band with 4n electrons is called valence band, and the upper band that has remaining 4n states which are empty called conduction band. At the equilibrium interatomic distance A0, this gap between the valence band and conduction band is called energy gap. So this energy gap is gap between the highest occupied energy level of the valence band and lowest unoccupied energy level of the conduction band. So this is how the valence band and conduction band form in a semiconductor. This energy gap for silicon material is 1.1 electron volt. That means we need 1.1 electron volt of energy for an electron to move from valence band to conduction band. This energy gap for different materials can be different. For example, energy gap for germanium is 0.67 electron volt. Energy gap for gallium arsenide is 1.43 electron volt. One more question arises here. Why this energy band is split in two bands at this interatomic distance? So we can find the answer using molecular orbital theory. This molecular orbital theory says that when two atoms come close to each other to have bonding between them to create a molecule, their outer orbitals tend to combine together and form a molecular orbit. So we will understand this formation of molecular orbit with the help of hydrogen atom. When we plot the energy level, it will have 1s orbital having a single electron, and this 1s orbital will be spherical in shape. So this is for one atom. Suppose there is another atom, another hydrogen atom that has same energy state 1s with one electron. When these two hydrogen atoms come close to each other, these two s orbital combine with each other, and there will be two different orbitals created. One is due to the positive interference of these orbitals, and another one is due to negative interference of these orbitals. When there is positive interference between these two orbitals, the overlapping and positive interference of these two orbitals causes the creation of the new orbital having lower energy state, that is called bonding orbital. And the overlapping of these two orbitals with the negative interference will create a higher energy level orbital, that is called anti-bonding orbital. Anti-bonding. So bonding orbital will have lower energy and anti-bonding orbital will have higher energy. In case of bonding orbital, all the electrons available inside this new molecular orbit is shared by both the atoms. And in case of anti-bonding orbital, there is a region between two atoms where no electrons are available for the bonding. That is why it is called anti-bonding. This is because of the negative interference of these two orbitals. There are few points that we keep in mind while creating this bonding and anti-bonding orbitals. The first one is the total number of molecular orbital formed will be always equal to the total number of the atomic orbital offered by the parent atoms. The second point is there are three types of molecular orbitals. The first one is non-bonding. Second one is bonding, and third one is anti-bonding. Non-bonding, bonding and anti-bonding. We have seen about the bonding and anti-bonding molecular orbit. This non-bonding orbital arises when there is a combination of two orbitals but not the overlapping. This happens when the orbitals have the wrong symmetry. They don't have the symmetry to interact effectively. The third point is filling of electrons in molecular orbit. So here the electrons are filled into molecular orbit in increasing order of the orbital energy. So first it will fill the lower energy level and then it will fill the higher energy level. So in case of two hydrogen atoms, both these electrons will occupy the lower energy state, and higher energy orbital, that is anti-bonding orbital, will be empty. This scenario of molecular orbital formation is for two atoms. Here two orbitals are combining to create bonding and anti-bonding orbitals. What happens when three different atoms combine together? There will be three different molecular orbital because molecular orbital total number is equal to the total number of atomic orbital of the parent atom. So we can plot it like this. For single atom of hydrogen, there is one energy level, or we can say there is one orbital associated with a single energy level, and we can plot it with number of atoms, energy versus number of atoms. So this is for one atom. For two atoms, it is divided in two. For three atoms, there will be three different molecular orbitals. For four, there will be four different molecular orbitals. When number of atoms increases, number of molecular orbital also increases. When it will become n, for n number of atoms, there will be n number of molecular orbitals with n number of energy states. When this number is very high, the energy gap between these molecular orbits becomes very narrow. It looks like a continuum of energy states, and this is called energy band. We should also see the filling of the electrons. So here one hydrogen atom will have one electron. A molecule of two hydrogen atoms will have two electrons in the lower energy state. With three hydrogen atoms, there will be three electrons. With four hydrogen atoms, four electrons. We can see here the lower energy states are getting filled and higher energy states are empty. When n is very large, almost half of this energy band will be filled and half of the energy band will be empty. So this filled energy band is called valence band and this empty energy band is called conduction band. When we apply the same theory in the case of silicon atoms, we can plot the energy versus number of atom diagram, same as here. This is for silicon atom. So here is the nucleus, 1s energy level, 2s, 2p, then 3s and 3p. Only the electrons in the valence shell participate in the bonding. So 3s has 2 electrons and 3p has 2 electrons. We know in the case of silicon atom, when the atom is in bonding state, these 3s and 3p orbitals create a hybrid orbital called sp3 orbital. And it has 4 unpaired electrons available for bonding with the other silicon atoms. There are 4 sp3 orbitals containing 4 electrons, 1 electron in each orbital. If we consider 2 atoms, then there will be 8 sp3 orbitals, and overlapping of these 8 sp3 orbitals will create 8 different molecular orbitals. So 4 anti-bonding orbitals and 4 bonding orbitals. This 4 bonding orbital will be occupied by the electrons. We have total 8 electrons for 2 atoms. So 1, 2, 3, 4, 5, 6, 7 and 8. So these 4 bonding orbitals will be occupied with electrons and these 4 anti-bonding orbitals will be empty. Similar to this previous case, when we consider n number of atoms, and that too when n is very high, this splitting of orbital will create a continuum of bands. The lower band has the bonding orbitals and all the orbitals are filled with the electrons. And the upper band is having all the empty states and it is not filled with any electrons, that is, it is empty. So here filled band is called valence band and empty band is called conduction band. And the gap between the highest energy state of the valence band and the lowest energy state of the conduction band is called energy gap. In this way, we can use molecular orbital theory to understand the splitting of the valence band and conduction band in the silicon material. In same way, we can plot this energy band diagram for other material also, but remember one thing, this energy gap will be different for all the materials. And this energy gap depends on many factors like atomic structure, valence band, hybridization, bonding, this initial energy gap, and the structure of the material. Now we will see and compare typical band structure or typical band diagram of insulator, semiconductor and metal at 0 Kelvin. In insulators, the electrons in the valence band are tightly bound to the nucleus of the atom. So this valence band is filled. That means all the energy states available in the valence band is fully filled with the electrons. This conduction band is empty and the gap between this valence band and conduction band, EG, energy gap, is very high. It is more than 3 electron volt for the insulators. For diamonds, it is 5 electron volts. Remember, there is no energy states that electron can occupy in between this conduction band and valence band. So the electron here must get energy more than 3 electron volt so that it can jump from the valence band to the conduction band. And because of this large energy gap, this insulator doesn't conduct the electricity. That means the electrons here in the valence band doesn't get enough energy so that it can go to the conduction band. The energy bands for semiconductor are same as insulator. Only difference is here the gap between the valence band and conduction band is very low. This valence band is fully filled with electrons, same as the insulator. Conduction band is empty, but this energy gap is very lower than the energy gap of the insulator. This relatively small band gap of the semiconductor allow for excitation of electrons from the valence band to the conduction band by reasonable amount of thermal energy or the optical energy. That is why even a slight increase in thermal energy, that is slight increase in temperature or the optical illumination, causes semiconductor to act like a conductor. In metals, these bands, that is valence band and conduction band, either overlap. This is overlapping of valence band and conduction band, or it is partially filled. Both these conditions are possible for metal. Either the bands overlap or they are only partially filled. So the electrons and the empty energy states are intermixed within the band so that electrons can move freely under the influence of the electric field. And that is why the electrical conductivity is very high in the case of metals. The semiconductor materials are very important and vastly used in electronic devices because it can act as insulator as well as metals. So at 0 Kelvin, a semiconductor we have as an insulator. This is because of the electrons in the semiconductor do not have enough thermal energy to overcome the energy gap and move to the conduction band, and it prevents the electrical conduction in the semiconductor. But when the temperature is increased or we give photonic energy to the electrons in the valence band, they gain enough energy, enough thermal energy to break their covalence bond in the valence band and jump to the conduction band. This allows the conduction of electricity, and the semiconductor acts as the conductor. So the energy gap for germanium is 0.67 electron volt. Energy gap for silicon is 1.1 electron volt, and energy gap for gallium arsenide is 1.43 electron volts. So till now we have studied that what is energy band, what is energy band gap, and how these energy band and energy band gaps are formed, and how it is different in insulators, semiconductors and metals. So this is all about the energy bands in semiconductor materials. Thank you.